All right. So we were looking at higher order equation. Applies for any linear differential equation with constant coefficients. It doesn't have to be second order. It could be third order, fourth order, but you just have to take a lot of derivatives depending on how many orders your differential equation is. So here you had to go all the way up to the fourth order. And if you plug it in, then you'll end up getting a fourth order characteristic equation instead of a second order. And then you'll have up to four, you'll always have four roots up to multiplicity. And then you just have each of those are homogeneous solutions, so that we saw that the general homogeneous solution would be the sum of all of those. So if you had a third order, you'll have to build the characteristic equation the same way we've done before, where the triple prime is a cubed and the double prime is a squared and so forth. Here I give you one of the factors, because otherwise it would be hard for you to factor a cubic. You'll use this factor that we know, so we know that r minus 1 is a factor. We just divide that into this to factor it, do a complete factorization. So here you're going to take this and you're going to say, I'm going to just take that and divide this factor into it. So r minus 1 is a factor. So if r minus 1 is a factor, you just do the long division. So I'll just say like this shows up right here. And then we'll just do the, sorry, that's kind of like writing on top of this. So I'll just go down. And then the way you do this is you look at this and say r minus 1, how many times can it go into r cubed? It goes in r squared times. And then I write that on top of the r squared so that it matches at the end. We know that the end happens when we get up to here. If you do r squared on this, you get r cubed, which is the whole point, minus r squared. And then the long division requires you to subtract this. So you'll say subtract this, and then you'll get r cubed minus r cubed, which is 0. That's the whole point. We were trying to match that so that it goes away. Negative 4r squared plus r squared is going to be negative 3r squared. And then you pull down one of these. You're going to look at how many times can r minus 1 go into the r squared? It's going to be, well, this negative 3r squared. I'm going to say negative 3r. That will multiply with this to give you negative 3r squared. Negative 3 times positive 1, a negative 1 is positive. And then you're going to say I subtract this. And then you'll get negative 3r squared plus 3r squared. That goes away. 5 minus 3 is 2. Pull this down. And then you have to do plus 2 here, because then 2 times r is going to give you 2r. 2 times negative 1 is minus 2. And then, of course, you're subtracting this whole thing. And you'll get no remainder, which is good. So your original, I'll just copy. So you're just this thing, we'll use black. So this thing right here, which was our original characteristic polynomial, will factor into of course, the r minus 1, which is is this one, because we know that 1 was a factor. And then we divided this and got that the other factor is going to be this quotient up here. So you'll have this. And so I'll put parentheses around that. So this is what it's saying, is that this factors into this. And then you can further observe that, so the r minus 1 is just going to stay. But this right here, r squared, minus 3r plus 2 actually factors further to r minus 1, r minus 2, because those work out. And so you'll have that your characteristic equation says that you need to have this equal to 0, which means that you have r is equal to 1 as a double, and you'll have r is equal to 2 as a single root to this. Okay, and then you unlike the one we had before where we had all these were distinct. So you had r plus or minus 1, r is plus or minus 2. You just build each of them. This one, you have one of them is a double. So I'll say like the one that's not a double, which is the r is equal to 2, that one's really easy. That's going to give you what kind of solutions? The using the same pattern we had. So all these right here, distinct real, we ended up getting these were the solutions. So this 2 is just by itself. So it would be, yeah. Yeah. So that's easier. The double root, at least one of them is really easy. One of them definitely better be C2e to the t, right? But what do you think the other one should be? Yeah. Yes, exactly. It's going to be what we remember about double roots is that one of them will be the one you'd expect, just, the same pattern we've seen before. But the other one was always multiplied by t with the same exponential. And we can justify that using reduction of order probably pretty soon. But for now, like, just remember that that's the thing we've been doing. So that's the homogeneous solution. Again, this is a third order equation. Given that it's a third order equation, we should expect up to 3, or not up to, just exactly 3 homogeneous solutions with different coefficients for all of them. So a triple prime should have up to C3. So we C1, C2, and C3. And so you'll have even though they may not be all distinct, you should have up to 3 roots up to including multiplicity. So a double counts as 2. Let's look at this one. So this one's a fourth order one. So we'll build the characteristic equation immediately by just using the r to the fourth plus 2r squared plus 1 equals 0. This factors to r squared plus 1 squared, actually. So it's going to have, it's like a, if you were to FOIL this, it would be r squared plus 2r squared. Yeah, this will be how it factors. And this gives us that we have the inside of this has to equal 0. So that means that the inside of this has to equal 0, means that r squared has to equal -1, which means that r is equal to plus or minus I. But it's actually like, suppose if this wasn't squared, it was just r squared plus 1 equals 0, then it would have been r is equal to plus or minus 1, plus or minus I, and that's it. But because this is squared, this is actually r plus or minus I, but it's a double root. Right? Because of this squared here. If this wasn't there, then it was just r squared plus 1 equals 0, and then you just move the 1 to the other side and just take the square root and we're done. But this is actually squared, so this is a double root. I plus or minus I is a double root. And we want it to be a double root because we need up to 4, because this is a fourth order equation. So you'd want this is a fourth order ODE. So you'd want 4 arbitrary constants. Not only we want 4 arbitrary constants, which would only happen if you have up to 4 four roots up to multiplicity. This just means that positive I is a double root and a negative I is also a double root. So you have two double roots, which is equal to 4 up to multiplicity. So let's first build the solution based off of if it wasn't a double root, then you just have plus or minus I. The solution for that would be, we know because it's a complex, no real part, it's pure imaginary, and the beta is equal to 1. So this would be the solution if we didn't have a double root. But it's a double root, so it's going to follow the same pattern we had before. What did we do before for a double root? One of them will be this, and then the other one will be exact copy of that multiplied by t. So this one will be an exact copy multiplied by t. So I'll just say, I'll move this over. So I'll just say there's this t that's being multiplied. But when I do a copy of it, I'm also going to change these to 3. Oops. To 3 and 4. Because that's what we did before as well for an exponential. We had c2 e to the t, the other one's also e to the t, but multiplied with a t, and then we know that in general, this coefficient may not be the same. So this is the same thing that you would do for this. Yeah. So we do have the 4 arbitrary constants that we needed for a fourth order differential equation. So the pattern here, you could digest this, is that if you have an nth order, so it can keep going higher than fourth order, where they're all constant coefficients. So, you see these are constant coefficients. So that means that these ANs and these are all constants. Then it will always give you an nth degree characteristic equation. And then if they're all distinct, that means literally all of them are distinct. Then you just do C1 R e to the R1, C2 e to the R2t all the way out, But if there's some that are actually has a multiplicity of 2 or 3 or 4, then that solution gets repeated that many times. And you multiply by t as many times. So that's why you have 1 factor of t here. And then if it's a multiplicity of m, then you're going to have to multiply by a t multiple times. And it turns out that if you have a double root, then you just have c1 e to the r1t, c2t e to the r1t, and that's it. If you have a triple root, there's another one and another one, and the final one will be just one less than the multiplicity. And if it's a complex conjugate, like if it's a pair of complex conjugate roots, the one we just saw, then it's like literally taking the solution without thinking about multiplicity, copying it, and then multiplying by t. And then if it happens to be, instead of a double, but a triple complex root, then you do the same thing as many times and multiply successively by more t's. So that's homogeneous. If you had a right-hand side that's non-zero, then you'll have to do this exponential. So there's a term here that's a degree 1 and a exponential multiplied together, but the point is this is not homogeneous anymore. So if it's a non-homogeneous equation, then you have here an exponential. And this is a degree 1 polynomial. So the left-hand side, it's x triple prime 4, 5, minus 2. Let's see, x triple prime minus 4, 5. So it's going to be the same as this one. So I'm going to just point out that the homogeneous problem is the same as this one that we just had, where we did polynomial long division. So I'm just going to copy and paste that solution because the left-hand side's the same as this one. So I'll just write that and say this is from problem 2.4.2. We'll get this is our homogeneous solution. And then I'll just label it as our homogeneous solution. So I'll just say x sub h is equal to this and maybe make it all blue. This is what we had from that problem before. So the homogeneous problem is not different from that, but now we have to build a particular solution. The particular solution is from the right-hand side. So you'll just say that you'll have x of p is equal to, it's a first-degree polynomial, so you're going to do a general first-degree polynomial multiplied by this exponential. But if you compare with our homogeneous solution, are there any issues? Yeah, so if you took this a naught and distribute it with this e to the t, that will match with this. But then if you also distributed this a1t with this, that would have matched with this. So you have these, and because there's two of them, you'll have to multiply by t twice. Resulting in your final particular solution to be t squared times the a naught plus a1t. Times the e to the t. And this doesn't have any issues because all the terms are at least t squared, e to the t. And that's not going to come, this only goes up to t, and then this term doesn't even have the same exponential. So this will be the correct solution form. And it only asks you for the correct solution form, so you don't have to plug this in. But if you were to try to find a1 and a naught and a1, you'd have to take the third derivative, the second, first derivative, second derivative, and the third derivative. Requires like product rule, and it's going to be kind of a lot of work. So we'll do one at the end, but I just want to get the right solution form for these. This one, the homogeneous problem we haven't done before, so it's going to be r cubed, the characteristic equation r cubed, minus 2r squared minus 5r plus 6 equals 0. And then I'm going to check if r equals 1, like last time, was a root. If you plug in 1 into this, it'll be 1 minus 2 minus 5 plus 6. 1 minus 2 is negative 1 minus 5. So this does equal 0. So r equals 1 is a root. Which means that r minus 1 is a factor, just like we had before, but the equation is still different. So you could do long division, but maybe it would be nice to try synthetic division if you've seen synthetic division before. The way it works is you write the coefficients in front of all of this. So r cubed is just a 1. There's a minus 2. There's a minus 5. And there's a 6. And then since r equals 1 is a root, or you could think of it as r1 is 1 is a factor, you'd put that right here. So you'd say this is 1 right here. Or you could say, because these are roots, that's going to give you this 0, this 1 right here. And then you say, okay, I'm going to build just going to draw a line, pull this 1 down. And then what you do is 1 times 1 is 1. You add these, it's negative 1. Negative 1 times 1 is negative 1. You add these, negative 6. Negative 6 times 1 is negative 6. And then you add this. This last one is for the remainder, so it's equal to 0. And then these right here are your coefficients in front of your of what would have been your quotient. So you'll have that this right here factors to, clearly r minus 1 is a factor. And then this synthetic division gives us that it's going to be r squared minus r minus 6. You just have 1 in front of the r squared, -1 in front of the r, and then -6. This goes in order. The last term here being the constant coefficient, the first order coefficient, and the second order coefficient. You could do polynomial long division, but it's easier maybe to do synthetic if you know that one. And so this factors to this, which of course has to equal 0. And then you just can notice that the green and can factor even further. So you'll have r minus 1. This right here factors to r plus 2 and then r minus 3 equals 0. So therefore you have 1, -2, and 3 are your roots. And then you have 3 distinct roots for third order equations. So you have your homogeneous solution is just going to be equal to the C1 e to the t plus C2 e to the -2t plus C3 e to the 3t. Then you build your particular solution, but this has 2 right-hand sides. So with this, we always did, right, build a particular solution for the first one. This is superposition. So superposition still applies even if it's a higher order equation. XP2. So we're going to build XP1. XP1 is going to be this exponential. So it's going to be a e to the t. Now, let's just make sure we get this completely right and then do the XP2. So this one, does it need to be changed? You got to multiply by t because this clearly matches with this homogeneous. So we'll have to multiply this one by t. So if you multiply this one by t, you're done because you don't need to multiply more than once. Don't multiply more than you need because you'll get the wrong solution form. So, but you do want to multiply by 1t. And so that's that. And that gives us our XP1. Like our XP2 is going to be built off of the the t squared term, which is second degree polynomial. So you'll build it as a general second degree polynomial. And this has no issues because none of these are polynomials. They're all exponential terms. So there's nothing that matches. So that one you don't have to multiply. You only multiply the solution that needs it, the sub-solution that needs it. Don't multiply everything because then you'll have the wrong solution form. So you'll have XP is going to be the superposition of these two. So you'll have one of them will be this one, which is the XP1 solution. And then the other one will be the XP2 solution, which is this one. Okay, and then I'll just note, yeah, of course, this is equal to your XP1. And this is equal to your XP2. So superposition still applies. Your multiplication by t only occurs to the subsolution that needs it. There's just now a third order equation. So your homogeneous solution will have C1, C2, and C3. So there's like 3 terms instead of 2. Put more potential for matching. So you might want to be careful with that. But it's still like the same idea. You build a characteristic equation which follows the same pattern we saw before where triple prime becomes r cubed. The rest of it's still the same. And then because you have a third order polynomial, third degree polynomial, it's a pain, it's a harder problem to find the roots. So let's look at this one is going to be a fourth order. This is x quadruple prime plus 2x double prime plus x. That actually might be one that we already did. It's this one right here. X quadruple prime, 2x double prime. So I'll just copy and paste this one. So the homogeneous problem is going to be the same as this, so I'll just paste it down here. So you see here, quadruple prime becomes r to the fourth, double prime becomes r squared. We did all of this, and we got this. So I'll just say that the work, we'll just delete the work, and then say that this was actually the homogeneous solution for this one. And I'll just say from example 2.4.9. We got this. I'll just label this as our homogeneous solution. And then we can just take it all and just say that this is blue for our homogeneous solution. So we have this. Now we have two right-hand sides. We've got this one right here. We have to separate these because they're not the same sinusoidal function. So if this was this is a 2t and this is a t. If this was a t, then you could actually get away with just building the particular solution from the one that has a higher degree polynomial multiplied to it, because that was one of the shortcuts we saw. Or if this was a 2t, then we could do it. But they're different sinusoidals, so we have to build two different we have to build two different so the form would be a general first degree polynomial times cosine of 2t plus b naught b1t times sine of 2t. Okay, this has no terms that match with our homogeneous because all the terms in our homogeneous are cosine of t, sine of t's instead of 2t's. So this one's done. The red one, the particular solution, second particular solution, is a second degree polynomial. So you'll have to build it off of, so I'll just say C0 plus C1t plus C2t squared cosine of t plus D0 plus D1t plus D2t squared multiplied by sine of t. And this one has conflicts because if you look at the C0 multiplied with this cosine of t, or even this D0 multiplied with this sine of t, that's like a constant multiplied by sine, cosine constant multiplied by sine. These together will match this stuff. Then if you multiplied, say, this C1 with this cosine of t and this CD1t with this sine of t, that would match these right here. So you need to multiply by t twice. That's going to be necessary to get all the terms to be distinct. Which means that I'm just going to copy this particular solution. And I'm going to put one giant bracket around it. And then put a t squared in front. Multiply by t cubed. There's no t squared up here, though. This is only up to t. Oh, right? Yeah. Yeah. So the t squared is enough, because then all your terms, the lowest will be t squared, and then the highest will be t to the fourth. This one, yeah, t squared is enough because it doesn't, it's enough to get rid of it. Don't multiply by more than necessary, but this t squared is coming from multiplying by t twice. And we need that, and then that's it. So our particular solution, second particular solution would be equal to this. So our full particular solution will be equal to the sum of these two. So you'll just say, I'm gonna take this right here and add it with this right here. And the idea is like this right here is my XP1, and this is my XP2. It's using superposition. And if you're worried about, these C0, C1s, and C2s, those are not necessarily going to be the same as these C1, C2s, and C3, and C4. I'm just going to put tildes on these just so that it's clear that since I use C0, C1, and C2 here, that you could skip the C's if you're worried about, like, of course, these are the arbitrary constants that are part of your homogeneous solution. These are not arbitrary. You would hypothetically find by plugging this into the differential equation. But in general, they may not be the same as the C1, C2, C3, C4. And the homogeneous, if you hypothetically also had an initial condition that, or if you need 4 initial conditions, I guess, for being able to find these 4 arbitrary constants. So I'm just going to put tildes on these so that it's clear that they're all potentially different. So that's the solution form for the particular solution using superposition. So we have this here. Okay, so let's look at this one. I added this one this morning, so I actually uploaded this probably 20 minutes before class because I thought it would be good to do a 5th order equation, but not just leave the solution form, but actually solve for the coefficients. So if you had a 5th order derivative, so it gets a little cumbersome to keep writing ticks. This is like 5 ticks, boom, 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 boom. But it would be like hard. I mean, that's not hard to read 5 ticks, but after a while, people are shorthanded like this. If you had like a 10th order differential equation or 7th order, then you don't want to keep writing these little. So if you had something like this, the characteristic equation is a 5th order equation. So it's going to be r to the 5th plus r cubed. That's it, because there's really just these 2 terms, and this has to equal 0. Turns out that even though it's a 5th order characteristic equation, it's not hard to factor because you just know that there's like r cubed that's common across these 2 terms, leaving you with an r squared plus 1 is equal to 0. So you'll have that r is equal to 0 is a root, right? And then r squared plus 1, that'll give you that r is equal to plus or minus I. Because you can just subtract by 1 and then take the square root. But this r is equal to 0 is not a single root. It's a what kind of root? It's a triple root, yeah. So that's important. So we need to say that this is a triple root because it's got the r cubed on it. So it's an r is equal to 0 is a triple root. We want 5 roots up to multiplicity. So you have plus I and minus I, that's 2. And you have 3 zeros, that's a total of 5. So you need that because your differential equation is a 5th order equation. So you need, not necessarily all distinct, but up to multiplicity, you need 5 roots. So your homogeneous solution will equal, so this triple root, it's like C1 e to the 0t, which is the same as C1, right? Because C1 times e to the 0 is just 1, so it'll just be C1. That's one of them. If this was a double root, the other one would be, what would you do? C2t, good. Now, what do you think the triple root's going to mean? Good. This is part of the summary we saw up here. So here it's saying that if you have r equals 1 is a root of multiplicity m, then you just keep successively adding. So, you know, for instance, let's just write on the slide here. For instance, if your R is equal to 2, let's say, is a triple, then you would have C1 e to the 2t. That's definitely one of them. The other one is C2 t e to the 2t, and the other one would be C3 t squared e to the 2t. You just keep multiplying by t as many times as the amount of, I mean, you need to build 3 if you have a triple, and they all have to be distinct, and you do that by multiplying by t successively. So that's if you had r is equal to 0 as a triple, this would be that. And then it looks like a polynomial only because e raised to the 0 is just 1. And then the other one is just plus or minus I. So that one's going to give you the imaginary solution, which is just C4 cosine of t plus C5 sine of t. So this is your homogeneous solution to this fifth order differential equation. You have C1 all the way up to C5, and you need that because this is a fifth order equation. Your particular solution is going to be looking at the right-hand side. You have a second degree polynomial here, so your particular solution will be a general second degree polynomial, a0 plus a1t plus a2t squared. Now, are there any problems? Yeah. How many times do I need to multiply by t? Twice? Any other? You don't want to multiply more than necessary, but you do want to multiply enough to make them all distinct. So if you multiply by once, then you'll have t cubed, t squared, and a t, but there's still this. If you multiply again, you'll have t to the fourth, t to the third, t squared. Oh, sorry, I forgot to, this is supposed to be squared, sorry. That's probably what's confusing. So multiplying by twice will still conflict with this. So how many times? 3 times, sorry, yeah. So you want to multiply by 3 times. So I of course, C1, C2, t cubed, yeah, t squared. So you want to multiply by t 3 times. Multiply by t 3 times. And if you do that, then your particular solution form will be to a t cubed, a naught t cubed plus a1 t to the fourth plus a2 t to the fifth. That's good because your lowest is t cubed, so you're above the t squared, and so you're good to go. And this is the right solution, particular solution form. But this one asks you to find the general solution. So let's actually see what the process would be. It's the same process we've done before. It's just a lot more work because you'll have to build the particular solution. We'll have to take the derivative 5 times. So you're going to do xp1 is going to be 3a0 t squared plus 4a1 t to the third plus 5a2 t to the fourth. That's just taking the derivative. Then you got to take another derivative because you got to go up to 5. So it's going to be 6a0 t plus 12a1 t squared plus 20a2 t cubed. It's just the power rule. And then xp triple prime will be 6a0 plus 24a1t plus 60a2 t squared. And then xp quadruple prime be, well, the first term goes away now because 6a0 is just a constant. So you're just left with 24a1 plus the 120t. And then you still need to take one more. I'm just going to label it as the 5th degree derivative. the first term disappears because 24A1 is just a constant. Sorry, I forgot to put A2 here. And then you're left with 120A2 for your fifth degree. And then we go all the way back to our original equation up here, and we're going to plug in. So xp to the 5 is 120A2. We skip all these terms, but just have the xp3 term. So that's going to xp to the triple prime term gets added to this. And this has to equal 60 t squared. Okay. And then we're just going to match. So we know that these have to match because these are the squared terms. We know that this is a t term that has to disappear. They all have to disappear. So the rest of them all have to disappear. So I'll just say these are my constant ones. They have to disappear. So from this, A2 has to equal 1 because 60A2 equals 60 will only work if your A2 is equal to 1. This right here, there's no t term on this side. So this means that A1 has to equal 0. And then this one says that my 120 A2 plus 6A0 has to equal 0. But we know that our A2 is 1. So that gives us that it's just 120 times the 1, because A2 is equal to 1. I'll just make it here. Just say like this A2 gets used, right? And then this is going to get added with 6A naught has to equal 0. So you're going to subtract by 120, and then you're going to divide by 6. So just write it. 6A naught is equal to negative 120. But that just means that your A naught is going to equal negative 20 because you're just dividing by 6. So our full solution, our general solution, will be equal to your A naught is, so you're going to have to use this one. This is the particular solution we're using, right? We're not using this one because that one's the wrong one. But now with this multiplying by 3 times, we've got A naught is equal to negative 20. So that's going to be negative 20 t cubed plus A1 is 0. So let's not write that one. A2 is 1. So it's going to be plus t to the 5 plus this giant homogeneous solution. That is going to be your general solution to this. Where we have the particular solution, which is this right here, and our homogeneous solution, which is this right here. But unlike the other problems before, I thought it would be good to go through the process of if had you been asked to not just leave the particular solution form, but like actually find the coefficients, you'd have to do exactly what we've done before. But the reason there's more work is because you'll have to take a fifth order derivative. And so just take the derivative successively. So this one was an easier one to take the derivative of because it was just a polynomial. And so you could just do the power rule multiple times. These other ones, it would have been maybe a lot harder because they might be product rules and stuff. But conceptually, this is what you would do for any of these if you were to actually solve for the coefficients A naught, A1, A2. You still have to do the homogeneous solution. The homogeneous solution is now in general a higher degree polynomial. So your characteristic equation will not just be quadratic. It could be up to 5 degrees, which means that you have roots that may not all be distinct, but up to multiplicity have to add up to 5, which means you have 5 different, so we'll show that they're linearly independent homogeneous solutions, and the linear combination of that will be the general solution that spans the solution space. And then you check if your particular solution has any conflicts. You just have up to 5 potential conflicts. So that's why we, in this case, had to multiply 3 times. And so next time what we'll do is for all these equations, we'll go back to second order. So we did like fifth order, fourth order, higher order stuff. We're going to go back to second order, and instead of looking at all these coefficients being constant, which is what we've been doing, we're going to think of those A, B, and C may not now may not just be by themselves. They might actually have like non-constant coefficients. Like if you put a t squared in front of this or a t in front of this, or some other versions of the non-constant coefficients. And we'll, go back to second order, but trying to solve it when we don't assume these are constants anymore. But yeah, I'll see you guys on Wednesday.